Alright, let me just check the video and audio. Seems to be working. Okay, so today's lecture is about the least squares problem. So this is 5.3 least squares problem, right? And you've perhaps seen this problem before in different contexts, and the idea today is to just use linear algebra and the tools that we've developed so far to find a solution of this problem. So I'm sure in your statistics classes, if you've taken statistics courses before, then you've seen the idea of normal equations and finding the least squares solution to a problem and so on and so forth. So let me just outline that problem. What is it that we're trying to solve? And then see how we can use the tools of linear algebra to solve that problem. So the problem is this. This is the problem. Sorry about that. So here's the problem. Let's say you have a bunch of points, right? And this is a bunch of points that you got from a data set. So this is your x, this is your y. And what you wanted to do is, of course, this doesn't look like a linear data. So what you want to do is perhaps fit a polynomial through it. And so let's say I want to fit some curve through these points that looks like this, right? So the idea is to find a curve of this sort that fits this equation. Now, let's suppose this is perhaps a degree 3 curve or a degree 2 curve. Let's say I want to fit a curve. So let's say I want some curve y equals to a naught. I want to fit some polynomial through these points, right? So a naught plus a1 x plus a2 x squared plus a3 x cubed, right? Now, because I have these data points, so let's say this point was x1 y1, this point was x2 y2, this point was x3 and y3. The minimum requirement that I want is at least this curve should go through these points, right? So I want the curve to go through these points at least, right? So at this point, what I want is to say that y1 should be equals to a naught plus a1 x1 plus a2 x2 whole squared plus a3, sorry, not x1. So this is x1. This is also x1 squared and this is x1 cubed, right? So notice that these are known. For example, if x1 is 2 and y1 is 3, then this equation simply says 3 equals to a naught plus 2 times a1 plus 4 times a2 plus 8 times a3. So don't think of it as a degree 3 equation in x1. Think of it as a linear equation in a naught, a1, a2 and a3. So basically my unknowns are a naught, a1, a2 and a3. And this is, of course, I've just shown you one equation. There are going to be several equations of these forms. So another equation will be a naught plus a1 x2 plus a2 x2 squared plus a3 x2 cubed is equals to y2. And so let's say there are m data points. So there are about m data points, and these data points, so let me just okay, so let's say there are about m data points. So the last point is xm ym. So essentially, so let me just write down this system. So this system is, the first equation was this was equation 1, this was equation 2, and the mth equation will look like a naught plus a1 xm plus a2 xm squared plus a3 xm cubed is equals to ym. And now, of course, I can write this as a large system. So I have a matrix that gives me coefficients. So notice, make sure that you understand that the unknowns here are a naught. So the unknowns are a naught, a1, a2 and a3, right? These are my unknowns for the problem. And the right hand side are points that I already know. So the right hand side is y1, y2, dot 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 up until ym, right? So this is an m by 1 vector, or rather I can say that this belongs to the m-dimensional real space. This belongs to the 4-dimensional real space, so this is a vector in R4. And of course over here I have all of these coefficients, right? So this was perhaps this could be anything. So how many of these I will have? So let's suppose in the first equation I have the coefficient of a naught was 1, so this is 1, coefficient of a1 was 2, so 2, coefficient of a2 was 4, so 4, 8. So I have 4 columns, and I'm going to have, because I have m data points, so I have m rows and I have 4 columns, right? So for this problem that we have an m by 4 matrix, which is A. Let's call this I don't know, let's call this let's stick with our original notations x. Notice that I'm calling this vector x, but this x vector, don't confuse it with x1, x2, x3, x4, right? Don't confuse it with these x's. This x vector actually denotes this denotes the vector a naught, a1, a2, a3. That's what I have to find, right? And so this is a, this is x, and this is b. And so essentially what I'm doing is I'm trying to solve this linear system. I'm trying to solve this linear system of equations, trying to find this x, right? And so notice that over here, since we have so many data points, like about m points, usually your data has lots of points, but what you want is you want to encapsulate all of that data with a few parameters, right? So usually in a data curve fitting problem or least squares problem, what you have is m is usually much greater than n, right? So this is, in other words, this is an overdetermined system. Okay, so we're talking about solving an overdetermined system. All right, so that's the setting, that's the problem that we want to find. And here's the clincher, that this system usually, systems like these overdetermined systems usually don't have a solution. And that's of course, that's definitely a problem, right? Because the idea is you can fit many different curves from these data points, right? I can even demonstrate that perhaps I can fit this curve from all of these data points, right? So it's not going to have a unique solution. I can perhaps think of another one that comes from below like this, does something funky over here, then does something funky over here, blah blah blah, but I'm just ensuring that it goes through all the points, right? So this is weird, this shouldn't have happened, but anyway, you get the idea. So we're not going to be able to usually find unique solutions to problems like this, right? So there's not going to be unique coefficients. Now of course I have taken a liberty here because I've drawn graphs of many different degrees, but the idea is there can be the same degree, different graphs of the same degree can also point through these points. So let me just so the idea is that this is not going to have a unique solution in most cases, right? That still holds. Okay, so that's the setting. So now what can we do if you can't find a solution? If you can't find a solution to the problem, then what can you do? What's the next best thing that you can do, right? And so if ax equals to b can't be found, where x belongs to the n-dimensional real space and b belongs to the m-dimensional real space, and notice that a is sort of can be seen as a linear transformation from Rn, from R, the n-dimensional real space, to the m-dimensional real space, right? So ax equals to b. This is not going to be true, right? So ax is not going to be equal to b, which means, in other words, if I take it to the other side, I am not going to be able to find a b minus ax which is equals to 0. So ax equals to b implies b minus ax equals to 0. Since there is no solution to this problem, there is no solution to this problem. So this, I can't make their this sum b minus ax to be equals to 0. So this b minus ax is going to be equal to something. So when I subtract this, let's call this r, right? This r is a function of x, and we call this the residual, right? And the idea is over here, if I can't find r to be 0, if rx is not equals to 0, maybe the next best thing that we can do is to minimize rx. That is, well, not rx specifically, but make rx as close as possible. Notice that this is a 0 vector, so b was in Rm, ax is also in Rm, so this is the m dimensional real 0 vector, right? So this 0 that I've written on the right hand side is actually a vector that contains m zeros, and I want this Rx, which is also an m dimensional vector, I want it to be as close as possible to the 0 vector, that is the m dimensional 0 vector. So in other words, I'm saying that the entries of this vector, this let's call Rx, let's make this vector, so Rx is perhaps R1, the first entry is R1, second entry is R2, R3, and so on. Let's say it has m entries, right? I didn't want to write it in a column form, so I wrote it in a row form and put the transpose here. So the idea is I want them to be as close as possible to 0. And in other words, that's just saying, if I want to be as close as possible to 0, that means its distance from the origin should be as small as possible, which means, how do you find the distance of a vector from the origin? You just find its magnitude, right? So we find Rx, the magnitude of Rx, which is R1 squared plus R2 squared plus R3 squared plus dot 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 Rn squared square root. Okay, and I want to minimize this. So that's the problem. We want to minimize the distance, the magnitude of this vector. And so let's make this problem into the form that people usually solve it. So the problem is, usually when you take a derivative of this vector, we're not going to be dealing with derivatives, but when you try to take derivative of this, you have a square root. You can get rid of the square root by saying that if you want to minimize Rx, then you can minimize, instead of minimizing Rx, you can minimize the square of Rx, because the square root function will not change the minimum of whatever the value is. So if I square this entire thing, then I will get rid of the square root, that means the square of this distance is just going to be R1 squared plus R2 squared plus R3 squared plus dot 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 Rn squared. And so this is an equivalent problem. If you minimize the square, then if you've minimized what's inside the square root, then you've also minimized the entire number, because the square root is an increasing function, remember that. So because square root is an increasing function, a strictly increasing function, so whenever you minimize whatever is inside the square root, you would have also minimized the square root. So for example, if I draw it, this is what the square root function looks like, right? So if you minimize what's on the x-axis, you will also minimize what's on the y-axis, right? So it's the same thing. If you minimize x, you're also going to be minimizing your y. So this is called the least squares problem, right? So least squares problem states that we want to minimize the sum of squares of the residuals. So I want to minimize this little entity here, that is r1 squared plus r2 squared plus dot 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 rm squared. This is something that we have to minimize, okay? And instead of doing any statistical tools, instead of using those ideas, we're now going to formulate this problem in terms of the linear algebra tools that we are familiar with, right? So this is where one of the applications of orthogonality is going to be heavily apparent, right? And so let's do that. Here's a theorem that tells us something important. But before I state this theorem, let's think about it visually a bit, right? So let's think about what's going to happen visually, right? Let's say this is Rn. This is my n-dimensional real space. This is where my x's come from. And let's suppose, again, we can visually see the matrix A as a bridge from the n-dimensional real space to the m-dimensional real space, right? Okay. And so, of course, this is going to have some, this is going to have an image, so there will be a range, there will be a subset. So there will be a subset usually, right, where this is the range of A, right? This is the range of A. So whatever, these are all the images of all the elements over here. So this is the column space, in other words, the column space of A, right? Now, of course, your situation is very simple if B lies in this vector space. If this B lies in this subspace, then of course you will have a unique solution, right? Because you will find some x whose Ax equals to B gives you the solution, but that's usually not the case. Usually what you have is B is outside this space and you're looking for you won't be able to find B here, but what you want is you want some P here, some P matrix, some P vector here, such that P is as close to B as possible, right? So let me just, let's go to the next page. And so the idea that I'm talking about, the idea is I won't be able to find Ax equals to B, but I can find an Ax equals to P such that P minus Ax is as small as possible, right? And perhaps I have, yeah, so such that P is as close as possible, oops. So I want P to be as close as possible to B, right? So in other words, I'm looking for B minus Ax is equals to the residual to be as small as possible, right? Okay, so the distance between this P and this X, let's call this distance between them is Rx. And I want to minimize this Rx such that I want to get this P as close as possible to B. Now I'm going to take a liberty here that I'm going to visualize this. Let's visualize this range of A, that is the column space of A, as a two-dimensional space, right? Of course, this is not always true. You're not going to get a two-dimensional space, but let's assume as visually that this is the space that you have. Let's say this is the range of A. And what I want, of course, is my vector B is outside. It doesn't, if it were inside, I could write it inside the plane, but since usually I won't be able to find a solution, what will happen is that I will get a vector that is sort of coming out of this plane, perhaps not at a 90-degree angle, but coming out at some angle. So perhaps if I draw it like this, right, so B is sort of coming out of this plane. And now if I want a vector in this two-dimensional space which is as close as possible to this B vector, then think about this. If I find its projection, something like this P vector here, such that this angle is 90 degrees. If I project this B vector, we talked about projections in the previous classes. So if I project, like I just find this x component, if I resolve this B vector into two components, one horizontal and one vertical, one which is inside this two-dimensional plane and one that is at a 90-degree angle to this two-dimensional plane. So if this is B, this is P, notice that I can write this as B minus P, right? So this vector is simply B minus P. You can figure that out using vectors. For example, if this is B, and if you want to do B minus P, then that's just simply putting a minus P over here, and B minus P is going to look like something like this. So this vector B minus P. So the idea is I want B minus P. It looks like B minus P is going to be orthogonal to my to P, but B minus P is also going to be orthogonal to this entire space, this range of A, so to speak, right? Of course, it's easy to visualize when it's two-dimensional and you're going out in the third dimension, but that's not going to be the case. You won't be able to visualize it, but the theorem guarantees you something very nice. And so here's a theorem that encapsulates this visual idea into a theorem for whatever dimension that you're working in. And so the idea is as follows. Here's the theorem. So if let S be a subspace of the m-dimensional real space, then for each B vector in this m-dimensional real space, there exists a unique P, this vector P exists in my subspace such that is closest to B. So this theorem guarantees me that there is some closest vector that you can find. So if you can't find B here, then you can find some vector P such that this vector is closest to this vector. In other words, if there is another vector, if y belongs to S, that is, there is another vector in the subspace that is not the same as the vector P, then the distance of B from y, this is how you write distance, right? So you subtract them and then you take the distance. So this is y, this is vector P, and so their distance is going to be B minus y, and you take the magnitude of this vector, right? This is the distance between these two vectors. The distance of B minus y, B from y, is going to be greater than the distance of B from P. So this is the same thing as saying that P is the closest vector. Any other vector is not the closest vector because it has a greater distance from B than P. So this is just saying P is the closest vector to B, right? And furthermore, the theorem is very nice. It tells you something else as well. Furthermore, it tells you that B minus P belongs to the orthogonal complement of S. So this vector, this B minus P that you're going to find, the distance of B from P that you're going to find, this B minus P vector that you're going to find, is going to be in the orthogonal complement. So this new vector, something like this vector, of course visually in 2 dimensions it's very clear it's going to be in the so if this was S, then this was in the orthogonal complement of S, because this is orthogonal to the entire space. But now this guarantees me that it's going to be in the orthogonal complement of S. Okay, and so let's prove this theorem before we can start using it. Let's go through a proof. So we know that if S is a subset, if S is a subspace, then Rm, this is something that we did in the last video. If you don't remember, you can go on and look at it. So the m-dimensional real space, if it has a subspace, then you can write any vector in the space as a direct sum. So Rm is a direct sum of S and its orthogonal complement, right? Which means any vector in this space can be written as S plus S complement. Now, since B is a vector in Rm, that means I can write B equals to P plus, so P plus Z, such that P is in the same subspace that I want and Z is in the orthogonal complement. Okay, all right. So first things first, I want to prove this. So furthermore, let me just encapsulate this. Furthermore, if P is closest, let me erase this. So let me rewrite this. The statement is saying, furthermore, P is closest if and only if B minus P is in the orthogonal complement. So this is something that we have to prove. P is closest if and only if B minus P is in the orthogonal complement. So we have 2 directions to prove. One, that B minus P is in the orthogonal complement, and the other direction is that if P is closest, then B minus P is in the orthogonal complement. Okay. So for the first one, we're going to prove in this direction first, that is if B minus P. So I am assuming that B minus P is in the orthogonal complement, right? And this is of course true. I have taken it by definition that this is true, because this vector is in S, this vector is in S orthogonal complement. So if I rearrange this sum, then I can see that P minus P is going to be equals to Z. So this vector is an orthogonal complement, and if this is another vector which is equals to this vector, then this entire thing is also going to be in S complement, orthogonal complement of S, right? So B minus P is nothing but Z over here. This vector is Z. Okay, this is something that I'm assuming to be true. So by this representation, this is something that I'm assuming, and now I have to show that if this is true, then P is the closest vector. In other words, this is something. So this statement needs to be proven, that for any other vector y, the distance will be greater. So let y be another vector in my subspace, then and y is not equals to P. So I'm taking a different vector. Then if I try to find the distance of y from B, what's this distance going to be? So, or rather residual square. If I want to minimize the distance, then I can minimize the square of the distance, right? So I want to prove that, just writing it on a separate side, that I want to prove, this is something that I have to show, prove that B minus y is going to be greater, the magnitude of B minus y is going to be bigger than the distance of B from B. Okay, all right. So let's break this down first. I'm going to introduce a variable P here, which represents my P vector. So B minus P plus P minus y squared. I have just introduced a minus p and a plus p, which means it doesn't change my sum, it should remain the same, but I've just introduced this and I've balanced it by introducing the negative and the positive together. Okay, and so this can be written as b minus p plus p minus y. Okay, alright, now here's the thing, this vector is in the orthogonal complement. That was my assumption. This vector p is in my subspace S, and this vector y is also in my subspace S. That means this p minus y is in my subspace S. And at this point I will use something called the Pythagorean law. So the Pythagorean law tells me the following. It tells me that if x is orthogonal to y, then x plus y is the same as x norm of x plus norm of y. And this is quite easy to see, and I'm not going to prove this, but perhaps I can just prove it for the case that I have in front of me. So let's take this example. So p minus p, so let's take this, we have p minus p plus p minus y whole squared. If you remember another definition of the norm, if you think about this, another definition of the norm of x, norm of r, can also be written, if you remember, it was written as square root of r transpose r whole squared. This is something that we did at the start of the orthogonality lecture. And so RTR, so you can write it as r transpose r. So norm of r squared is that. Now if I want to take this b minus p plus p minus y, then I can write this as this vector transposed. So I have b minus p plus p minus y transpose multiplied by, so I'm just doing r transpose r, right? So multiplied by the same vector again. So the same vector is b minus p plus p minus y. Okay, and so what does that get me? It gets me the following. I can put the transpose on these individual vectors b minus p, because the transpose is linear transformation. I can separate the transposes, and this is being multiplied with p minus p plus p minus y. Okay, which gives me b minus p transpose. Now I can multiply these terms times b minus p plus 2 times, let me just write p minus p transpose p minus y plus p minus y transpose times p minus y. Over here I've used the fact that b minus p transpose p minus y is the same as, is equals to p minus y transpose times p minus p. And here's the important thing, since this was in the orthogonal complement of S, and this vector b minus y was in S itself, these two vectors should be orthogonal to each other. When two vectors are orthogonal to each other, then their inner product, their scalar product, is going to be 0. So b minus p, from this fact I know that b minus p transpose p minus y has to be 0. And so this gives me, this is simply b minus p. This is, if you think about this, this is just the norm of p minus p, that is the magnitude of this vector. This I know to be equals to 0 because these vectors are orthogonal, plus we have p minus y, the norm of p minus y squared. Okay, so what I've shown essentially, I wouldn't have had to do all of this if I had just proven the Pythagorean law. So you can just if you just know the Pythagorean law, then you know that x plus y should be equals to norm of x plus norm of y, right? So sorry, there's a squared here. Okay, and so now this tells me that b minus y squared is equals to b minus b norm squared plus b minus y squared, right? Now think about this term over here, this over here is a positive quantity because it's just the sum of squares of some numbers, right? Which means it guarantees me that b minus y squared is going to be bigger than b minus b squared, which guarantees me that if the squares are bigger, that means b minus y is going to be bigger than b minus b, right? So I've given a guarantee that if this y was a different number from p, in other words, y is not closest, p is the closest vector. That is, any other, for every other y, their distance will be distance of b from y must be bigger than the distance of b from b, and that's exactly what this statement is saying, which completes the proof in one direction, right? For the other direction, I'm going to use a proof by contrapositive. So the other direction tells me that if p is closest, then b minus p is in the orthogonal complement. And to prove by contrapositive, here's what I'm going to do. I'm going to prove that if b minus p is not in the orthogonal complement, then p is not the closest. P is not the closest vector. So I can use this fact, and so let's take this. So let's suppose let q, so this not closest vector, this vector that is not the closest vector, I'm going to call this vector to be q. Let there be a vector q such that b minus q is not in the orthogonal complement. Well, we've already seen that we can prove b minus q. I can write this immediately because the same argument that we did before, we find the distance of b minus q squared and we do the Pythagorean law, and I can immediately show that if b, it's going to be bigger than b minus p for this p which is in the orthogonal complement. So that means that if b minus q is not in the orthogonal complement, that automatically means that q is not the closest vector. Okay, so that finishes my proof for this theorem that tells me that not only does this closest vector exist, this theorem guarantees me that this closest vector p exists, but also that b minus p, their difference, b minus p, is going to be in the orthogonal complement of S, and that's an interesting thing to have because it will help us find it. Okay, all right, so now that the proof is done, the question is, what do we do with it, right? How do we solve it? Before we go to the practicality of it, let me just mention the special case. So a special case is what if B was in the subspace? So far we've considered that B was not in the subspace, right? What if B vector that I'm assuming is outside the subspace, what if it was inside? Well, if it was inside, then of course, what's the issue? So a P vector, any vector in Rm, since P is in Rm, it can be written as P plus Z, where P is in S and Z is in the orthogonal complement of S. But of course B can also be written as B plus 0, and this I know that this vector I have written it as a sum of two vectors. One of them is S and the other is 0 vector, which is also in the orthogonal complement. 0 vector is in every subspace. So since I know that the orthogonal complement is a subspace, 0 vector has to be there. Now notice that what I have gotten are two different representations for B. And by the previous video I showed that this direct sum representation has to be unique. That is, this direct sum representation can't be different, which means that P must be equals to B in this case. So in other words, it's saying a very trivial thing. It's saying that when you have this vector inside your subspace, the closest vector that you can find is itself, right? So the vector that's going to be in this space that's going to be closest to the vector is going to be itself, right? So let me just, if that's not clear, let me just draw a diagram. If my vector is in this subspace and I'm looking for another vector which is closest to this vector, which is also in this subspace, then I can just use this vector because this is already in the subspace. Okay, and so there's nothing special about this. Well, there's nothing complicated about this case. You can immediately set P to be equals to P and you're done. So you can just find that vector. Okay, so now that we're done with all of this discussion about how to know that this closest vector exists, how do we find it? Question is, how do we find it? And also notice that what we're interested is not P. So what we're looking for is a solution to Ax equals to B. Since I can't find a solution to this, I'm looking for a solution Ax hat is equals to P. So how can I find this P, and then using that, how can I find this solution, the closest vector that can give me to the closest vector, right? So let's go one more time back to the diagram. And so there must be some x hat that goes to this P. So I'm saying Ax hat goes to P. And what I'm interested in is not just in P, because P is just the closest vector here. I want some solution. To solve this equation, I want this x hat. And so the question is, how do we find this x hat? So let's begin to answer that question. And so here's the idea. The idea is as follows. I want a solution. So B minus Ax. So I said before that B minus Ax is not going to be equals to 0. It's going to be equal to some residual, right? And so if I want to minimize it, then I use this B minus Ax hat, because I know this. If I use P here, then this is going to give me the smallest distance, right? So P is just P minus Ax hat is equals to the residual, right? So I've written it in two different forms, that this Ax hat equals to P is something that I'm solving. Ax hat is equals to P is what we're looking to solve. So here's the important thing. B minus P is in the orthogonal complement of S. That is something that we've already established. And we are also seeing that this B minus P is just the residual. Then that tells me that the residual is in the orthogonal complement of S. Now here's the interesting thing. This orthogonal, this S subspace, what is this subspace that we're talking about? This subspace is nothing but the subspace that we were talking about was nothing but the column space of A. This is the subspace that we want to find P in. So B minus P is actually in the orthogonal. This S was just the column space of A, so this B minus P must be in the orthogonal complement of this S. So S is just, the idea is that S is simply the column space of A. And so I'm looking for an orthogonal complement of the column space of A. And at this point, if you have the previous lectures fresh in your mind, then you will remember something interesting, that firstly Rx needs to be in, so at this point Rx, this residual vector, needs to be in the orthogonal complement of my column space of A. And recall that the column space, the orthogonal complement of the column space is nothing but the null space of A transpose, right? This is a relationship that we saw in the previous video. And so if Rx is in the orthogonal complement of the column space of A, that automatically means that Rx is in, Rx belongs to the null space of A transpose, right? What does that tell me? What's the null space of A transpose? The null space of A transpose, the null of A transpose is just all of those vectors y such that A transpose y gives me the 0 vector, right? A transpose y gives me 0. So that means if the residual vector is in the null space of A transpose, then A transpose times the residual vector should give me the 0 vector. Okay, so let's just think about what this equation is saying. Just to be clear, this A transpose, if A was an m by n matrix, that's what we started off with, then A transpose has to be an n by m matrix. The residual vector, we've already established that this is in the m dimensional real space. So this equation, this 0 vector has to be in the n dimensional space, right? So n minus m times m minus 1 is going to give me an n times 1 vector. Sorry, not m minus 1, m times 1. So this vector has to be an n by 1 0 vector. Okay. And so, well, what is Rx? Rx I already know. It's B minus Ax. So let's substitute that equation. A transpose B minus Ax hat has to be 0. And so let's just rewrite this equation. A transpose B minus A transpose Ax hat is equals to 0. So what I'm looking for is I want to solve the system ATAX hat is equals to A transpose B. Okay, and so let's for a moment think about this system. What does this system actually mean? A transpose was n by m. This is an n by m matrix, and A matrix is m by n, which means A transpose times A is going to give me this little thing here is going to be a square matrix, n by n. I already know that x hat has to be in the n dimensional real space, so this equation does make sense in that this is coming from Rn, so this has to be n by 1, because we knew that we're looking for x hat in the n dimensional real space. If you don't remember that, that's just coming from the fact that x hat was in this space in Rn, right? Okay, I keep coming back to this diagram. Let me just copy this and I will paste it every time I need it. Okay. Alright, so this has to be an n by 1 vector. So the left hand side gives me an n by 1 vector, and think about this. B was in the m dimensional real space, so this is an m by 1 vector, and A transpose is n by m, so the right hand side is also n by 1. So the equation makes sense. So far I've just verified that the equation makes sense. I can write this perhaps in a different way. I can just say that this is a system that's solving B x hat is equals to C, where B is such that B is A transpose A and C is A transpose times B, right? So coming now from solving this overdetermined system, this where it had m by n rows, and this was a very disbalanced system that we're trying to solve. Instead, we found a system, a square system. This is n by n matrix, right? So this is a nicely balanced square system where it has n rows, n columns, and the right hand side is also n by 1. So everything is n here, n rows here, and n vector here, right? So this is a square system that we now have to solve. Okay. All right, so we've reduced the problem to a nicer, perhaps, problem, but we still haven't solved the problem, right? And now the question that we asked before, all of these questions that we kept asking, so from finding P to be the closest vector, notice that I keep changing the question. Now the question has become, I need to solve Px hat equals to C. This is the equation that I have to solve. And by the way, this system that I've written over here, these are also called. So the system that we're looking to solve is A transpose Ax hat equals to A transpose B. This is called the system, these are called the normal equations, right? So this is the system of normal equations that we have to solve. Okay, and so question is, of course, when do the normal equations have a unique solution? Because I want to solve this system, I want to find the fact that when do these normal equations have a unique solution, because it's not guaranteed. What if this is a singular matrix? If it is singular, then I'm done. I can't really solve this. So if it's non-singular, then I know that there's going to be a unique solution to this problem. Okay, so the answer is when A transpose A is non-singular. Okay, so the question is, when is A transpose A non-singular? And that brings me to this theorem. So we have another theorem to our rescue, and so this is what the theorem states. The theorem states that there is, let A be an m by n matrix, then ATAX equals to A transpose B has a unique solution, if it has a unique solution if A has rank n. This is the important bit right here. So this fact guarantees me that if I can guarantee that A is in rank n matrix, then I'm done. Okay, then X hat will be a unique solution that I can find. So I can find X hat to be equals to A transpose A inverse A transpose B. I can find a solution to this system. So the inverse will exist only when A has rank n, right? So let's try to just prove this little fact. If we can prove this, then we can prove that there is a unique solution. We can invert this A transpose A matrix and blah blah blah. Okay, so let's not waste any time. Let's jump into the proof, and let's say let Z be a solution. to the normal equations, which means I am saying that Z is a solution to A transpose A, X hat is equals to A transpose B. That is, if I substitute Z in place of this vector, then both of these sides will be equal. Now, what does that tell me? That tells me that, let me correct that, I'm making a mistake. So I want, let Z be a solution to the homogeneous equation, or rather system of equation, A transpose A, X equals to the 0 vector. I want Z to be a solution of this homogeneous system. Now, why am I doing this? Let me just clue you in on why am I doing this. The idea is, remember that when Ax equals to 0 has a trivial solution, then Ax equals to B has a unique solution, for all B, right? So if I can guarantee that the homogeneous system just has a trivial solution, these were equivalent conditions, that trivial solution means unique solution for the non-homogeneous problem, which means A is non-singular, and so on, non-singular, and also that determinant of A is not equals to 0. These were all equivalent conditions that we've done before, and that's the idea that I'm using, that instead of showing that this has a unique solution, I'm showing that the homogeneous problem has a trivial solution. Okay, and so this is where I'm going with this. Okay, so how do I prove that the homogeneous system has a unique solution? So I want to show that Z is the trivial solution. Okay, so how do I show this? Since I have to show this, let me just remove it, because I'm not assuming this. I have to get to this fact using the facts that I have. Okay, so if Z is a solution, all I know, if Z is a solution, then what do I have? Then I have that I can rewrite this equation, A transpose AZ is equals to 0. Okay, now what does this tell me? Think of this as just one vector. If this is one vector, then this is just the homogeneous equation A transpose Y equals 0, which is just that this is a solution to the homogeneous problem, which means, in other words, I'm saying that AZ, well, over here we say that Y is in the null space of A transpose. Then over here I'm saying that AZ is in the null space of A transpose. All right. So that's one of the facts that we have. AZ is in the null space of A transpose. But also notice that AZ is in the column space of A, and that's actually a trivial thing to say, because any vector X, if I multiply it by A, I'm just taking this vector to its, if you think about it, if I take X and I multiply it with A, then I'm just taking it to the column space of A. This is column space of A by definition. Ra is just contains every vector such that every vector B such that B is equals to A times X. It contains every vector of this form, which means A times Z is also in the column space of A. Now what does this tell me? AZ is in the null space of A transpose, and it is in the column space of A, which, if you remember, both of these are orthogonal complements of each other. So in other words, I'm saying that not only is it in the null space of A transpose, it is also in the null space of A transpose the orthogonal complement. The column space of A is the same as the orthogonal complement of the column space of A. So in other words, I'm saying that AZ is a member of a subspace and its orthogonal complement. And this, you should recall that always, that the orthogonal complement and the subspace itself have nothing in common. Their intersection is just the zero vector, which guarantees me the following. It tells me that AZ must be equals to 0, that this column space, this column vector has to be 0. And question, what's the solution? What's the solution to AZ hat equals to 0? When does it have a trivial solution? When does it have only the trivial solution? And notice it has a trivial solution when I want to solve AZ hat. So I want AZ equals to 0. This is just saying that I have a vector Z, that I have a vector Z that I am multiplying by A, taking it to another space, taking it to its column space, and actually I want to map it onto not onto any other vector but on just as 0. So in other words, I am saying, if you view, let's expand this. So it had m rows and n columns, right? So A was m by n. So it has first column A1, second column A2, third column A3, dot 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 AN times Z has to be the 0 vector. Now if let Z equals to Z1, Z2, Z3, dot 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 Zn. Now this just gives me, I can rewrite this as nothing but a linear combination, Z1 A1 plus Z2 A2 plus Z3 A3 plus dot 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 Zn An equals to 0. And this is just saying that the linear combination is 0, which is closely related to the idea that this is equals to 0 has a trivial solution when A1, A2, dot 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 An are linearly independent. And when do we have linear independence? We have linear independence when the rank of A is equals to n, that is, it has n linearly independent columns, right? So if you remember, rank is nothing, rank of A is nothing but the dimension of the row space of A, which is incidentally equal to the dimension of the column space of A. Which means the column space of A, these columns has, the column space of A is n dimensional. So if we are saying n, that means it has n dimensional span, which means all of these n vectors have to be, these A1 to An have to be linearly independent, because if they're not linearly independent, they can't have an n dimensional span. If they're linearly dependent, their span will be less than n dimensions. So let me just, and at this point our proof is done, just by the way. So let me just restate what happened. When A has rank n, so when A has rank n, then AZ equals to 0 has only the trivial solution, which in turn guarantees to me which guarantees to me that ATA z equals to 0 also has only the trivial solution, which in turn guarantees to me that ATZ, or rather, if the homogeneous system has a trivial solution, then the non-homogeneous system A transpose B has, or rather, let me not skip the steps, let me say that if I have a if this non-homogeneous system ATAX equals to y has a unique solution, for all y, then ATAX hat has to has a unique solution as well. Because if it has a unique solution for any non-homogeneous right hand side, then it's definitely going to have a unique solution for this particular non-homogeneous side. And so this has a unique solution, then x hat you can inverse. So in other words, this matrix is invertible, and you can do A transpose A inverse A transpose B. And so now you have a guarantee that this is a unique solution, and you can find it just by solving the system. So at the end, all you have to do is to solve. We have a guarantee now, so we just solve the system for x hat, right? And that will give me what? Let's just it will give me what? If I have, it will give me actually P. If I have x hat and I multiply it with matrix A, then that's just the same as P. Ax hat is being mapped, so remember what was happening. I found an x hat, which if I multiply by A gives me the vector P. And so in other words, P is equals to A times this x hat. I can just copy paste from here. So this x hat was nothing, so this is A times x hat was A transpose A inverse A transpose B, right? Just as a notational thing, we call this is called the projection matrix P, because what you see, if you combine these two equations, the left hand side and the right hand side, I can say that P is equals to the projection matrix times P. That is, if I take this B, if I take this vector B, and if I multiply it by P, I get capital P times B gives me this vector. So essentially, this matrix, when you multiply it with P, it projects it onto the vector which is closest to it, the orthogonal sort of vector, or the orthogonal projection. So P is the projection of B onto the column space of A, and that finishes it. So this lecture was more about proving that you can use linear algebra to solve this system. So there were two theorems that we proved. One was that the first theorem that we proved was that there is a closest vector that you can find, and the second theorem told me that if you're guaranteed that you can solve these normal equations to find this closest solution, right? So instead of solving it for x, so instead of Ax equals to B, I can't do this. I can do Ax hat equals B. So this is this system that I solve, and I'm guaranteed that I can find a solution to this problem. Okay, and that completes the lecture. So once you have this x hat, you can use that. Let's circle this back to this curve that I have. So if I have solved, remember that the x hat was a proxy for A0, A1, A2, A3. If I can find this x hat, then I have essentially found that nice little curve that I wanted, that orange curve that passed from all of these points and had the minimum residual, right? It's, of course, it's not going to pass from all of these points because I don't have a solution for ax equals to b. If it were able to pass, just to make sure what we are talking about, if it were able to pass from all of these points, then the residual would have been 0, exactly 0. But I couldn't find ax hat equals to b. What I did find was ax hat equals to p, such that it's not going to be able to pass through all of these points. So let me draw the diagram again. Unfortunately, it won't be able to pass from all of these points. That's not something I can guarantee, but it will pass from some of them, or it will be such a curve that these distances, this residual, this residual, this residual, this residual, these will be as small as possible. Their sum of squares will be minimum. Okay, so if the distance of a point, from the curve, let's say this distance, let's call this, if this was r1 and the distance over here was r2, the residual here was r3, r4, then we're going to minimize these distances by solving ax hat equals to p. Okay. Alright, that's the end of the lecture. If there are any queries, if there's any confusion, let me know in the comments or on Piazza, or send me an email. If you ask it on Piazza, that's better. Right. Thank you. Have a good day.